In this second block of this series, we're going to talk about derivatives in multivariable calculus. This first video, though, will be a short repetition of derivatives in single variable calculus. This is to have these concepts fresh in memory when we extend them to several variables. Focus in this video will be on the definition of the derivative and how to work with it. Let us start with what the derivative is. Start by drawing a curve. The short answer is that the derivative is the slope of this curve, but let's do it more mathematically strict. Start by selecting one point x on the curve. The curve will have value y of x at this point. Continue and define a second point at position x plus delta x, where delta x is one step in the x direction. The function value at this new point is y of x plus delta x. Define the slope of the curve as the difference in y value over the difference in x value, or delta y over delta x. The distance between the points in the x direction will be delta x. Call the distance in the y direction delta y. The difference in the y direction delta y is y at the position x plus delta x minus y at the position x. Next, we're going to take the limit where delta x goes to 0. Let us illustrate it graphically. When delta x goes to 0, we get the slope at the position x. This is the definition of the derivative. To indicate that we have let delta x go to 0, we will change the notation and replace delta with the letter d. The derivative of y with respect to x is therefore called dy dx. Let's illustrate how the definition of the derivative works by doing an example. Set y of x is 4 minus x squared, which is the graph we see in the figure. Start from the definition of the derivative. Insert expression for the function as the y of x term. And simplify by placing the minus inside the parentheses. Next, we replace the expression for y of x plus delta x. Note that we have to write x plus delta x everywhere where it's written x in the function. And we get x plus delta x squared in the expression. The two 4's will cancel each other. Expand the parentheses. And write the minus sign inside the parentheses. The x squared term will cancel. We can divide by delta x. This is valid as delta x is very small, but it only approaches 0. It never becomes 0. And finally, we can let delta x go to 0, which removes this term. The final result is that the slope is minus 2x. I will assume that you already are familiar with this result and know how to calculate the derivative of our basic fundamental functions in math. But it's still good to have a repetition of how to derive the expressions. To be a bit more mathematical, we can talk about the derivative operator d dx. This operator will act on the function y of x. The benefit of thinking of it as an operator is that we can replace y by the expression for the function instead. Now we have that dy dx is d dx of 4 minus x squared. And then we could calculate the result by the traditional formula for taking derivative of polynomials. Our next concept is a second order derivative. This is when we apply the derivative operator twice. To get a shorter notation, we often write it as d to x dx squared. If we were to calculate for our example, start from the expression for the second order derivative, then insert equation for the derivative. And finally, take the derivative of this expression. To illustrate the derivative more, let us switch to a slightly more advanced function, a cubic polynomial. We are now going to draw the derivative of this curve, which is the green line. The more slope we have, the larger value of the derivative. We can also write down the derivative as x squared over 2 minus 1. Next up, let us check the slope of the derivative to get the second order derivative, which is the purple line. The equation for the second order derivative is simply x. Let us take a look at how the function, the derivative, and the second order derivative are connected. If we move to the first point where the derivative is 0, we see that there is no slope for the function. The function, the blue line, has a curvature though. If we would be traveling along the blue line, we would be turning to our right. This is connected to a negative second order derivative. If we continue to x equals 0, we have a negative derivative, but the second order derivative is 0. This means that if we travel along the blue curve, we would be going in a straight line at this point. Let us continue to the next point where the derivative is 0. Here we have a positive second order derivative. This means that if we travel along the blue curve, we would now be turning to our left. The conclusion is that the second order derivative is associated with how much the curve turns at a given point, which we can call the curvature of the curve. Next up, I want to mention how we can use the derivative to approximate the value of neighboring points. Assume that we know the value of the function at point x and want to approximate the value at x point delta x. We can use the definition of the derivative to create an approximation. Start by dropping the limit expression, which turns the equality into an approximation. Then multiply both sides with delta x and move y of x to the other side. This is a simple approximation of y of x plus delta x, which we will use in many mathematical derivations. For those familiar with Taylor series, this is a first order Taylor series expansion of the function. Let's apply this result by deriving the product rule for differentiation. Take the derivative of f of x times g of x. The definition of the derivative states that we should first input the function value at x plus delta x, then subtract with the function value at x, and divide the result by delta x. Let's use our approximation for the f of x plus delta x term. And use it for g of x plus delta x. Expand the parenthesis. F of x times g of x will cancel. Divide by delta x. In the limit where delta x goes to 0, this term becomes 0. And we have the product rule, which states that to calculate the derivative of f of x times g of x, you first take the derivative of f of x multiplied by g of x, plus f of x multiplied by the derivative of g of x. A quick example of how to apply this. Assume that you have y of x is x squared times sinus x. We can define f of x as x squared and g of x as sinus x. Next, we calculate the derivative of f of x to 2x. And the derivative of g of x is cosinus x. The derivative of x squared sinus x can now be obtained from the product rule by inserting these four expressions. And the final result become 2x sinus x plus x squared cosinus x. The next derivative rule that we will use a lot is the chain rule. Assume that we want to take the derivative of function g with respect to x. However, now we assume that g is a function of h, where h is a function of x. If we write the definition of the derivative, we get the following expression. This time, we will go back to the other notation for the slope and write the derivative as the limit of delta g over delta x when x goes to 0. Let's use this part instead for our derivation. Let's introduce a small change in the variable h by multiplying and dividing with delta h. Now we can let delta x and delta h swap places. We can then use that when delta x goes to 0, both delta h and delta g will also go to 0. Hence, in the limit we can replace delta with the derivative operator d. This is the chain rule for differentiation. To demonstrate it, let us show an example. Let y of x be sinus x squared. We can identify the outer function g of h as sinus h. The inner function h of x will be x squared. The derivative of g with respect to h is cosinus h. The derivative of h with respect to x is 2x. To get the final result, we insert the two derivatives according to the chain rule. Next, we replace the expression for h with this equation x squared. And the final results become cosinus x squared times 2x. For completeness, I will also mention the quotient rule, which is the derivative of f of x over h of x. Start by rewriting it as the derivative of f of x times 1 over h of x. Now we can introduce a new function, g of h, as 1 over h. Its derivative with respect to h will be minus 1 over h squared. If we want the derivative of g with respect to x, we can use the chain rule. Insert expression for dg dh. Next, we can notice that our expression is the derivative of f of x multiplied by g of x, and we can use the product rule. Insert expression for g of h. And insert expression for dg dx. Here it's common to multiply and divide by h. And then write the expression with a common denominator. This is the final example for our single variable calculus derivative repetition. Next up, we will go through how we can extend the derivative to multivariable calculus. Thank you.